Okay, so hello everyone. In this video, we will discuss memory management in operating system. Although it is a very huge topic, so we will cover it in details with 4 to 5 lectures. So in this video, we will first discuss introduction to memory management, then memory management techniques, in which we will discuss fixed and dynamic partitioning in details. So let's move on to the introduction to memory management. Memory management in operating system is a fundamental functionality that manages various types of memory efficiently. In our laptops or our computer systems, there are different types of memories available like RAM, hard disk, registers. So the primary focus of memory management is to handle these memory resources in the most efficient manner possible. So we majorly concentrate on RAM because it constitutes the majorly of the memory that the system actively works with. Now let's understand this with a simple diagram. We have a CPU whose purpose is to execute instruction and programs. A program is essentially a collection of instructions that need to be executed one by the CPU. The CPU is directly connected with register and cache memory, and it's also connected with RAM, which is also known as primary memory. RAM is then connected with secondary memory. There is an important principle here. CPU is very fast while secondary memory is very slow. That's why we cannot directly connect the CPU with secondary memory. Instead, we place faster memories like registers, cache and RAM between them. Now if we increase the size of RAM, cache or registers, it directly affects the cost of the system. Higher memory means higher the cost. Now here is the crucial concept. All programs that need to be executed are stored in secondary memory. For the CPU to execute these processes, we must bring them from a secondary memory into the RAM, so the CPU can directly interact with them. This is essential because CPU is not directly connected to secondary memory. While we could use cache and register, their size is much smaller than RAM. Registers are typically in kilobytes. So this leads us to an important concept called degree of multiprogramming. Multiprogramming means bringing multiple programs from secondary memory into RAM simultaneously rather than loading just one program. Why do we need multiple programs? Because higher the degree of multiprogramming, higher the CPU utilization. Let me explain this with an example. If we bring only one process P1 into RAM and CPU start executing it, the process might make an IO request during execution, perhaps to use a printer, scanner or read a file from secondary memory. When a process make an IO request, the CPU becomes free at that time because P1 exits CPU and goes to perform IO operation. This makes CPU idle, which reduces system efficiency and performance. The solution is to keep more processes in the RAM. When one process goes for IO operation, CPU can immediately switch to another process, maintaining high CPU utilization and system performance. Let's solve numerical example for clarity. Assume we have a RAM of size 4 MB and one process of size 4 MB. How many processes can be accommodated? Only one, because RAM size equal to process size. Now there's a probability K that represents the time a process is spent on IO operation. If a process does IO for k time, then it executes in CPU for 1 minus k time. Let's say k is 70%, meaning 70% time is spent on IO operation. So CPU utilization is what? 1 minus k, which is equal to 30%. Now if we increase RAM size to 8 MB while keeping process size at 4 MB, we can accommodate two processes. Now when both processes perform IO operations simultaneously, the probability becomes k square. So CPU utilization becomes 1 minus k square is equal to 1 minus 0.7 square, approximately 76%. If we further increase RAM to 16 MB, we can accommodate 4 processes. The CPU utilization becomes 1 minus k to the power 4. Now approximately this will be 94%. Now notice here how CPU utilization increases dramatically as we accommodate more processes. This demonstrates that increasing RAM size allows more processes, leading to higher CPU utilization. Now memory management involves bringing maximum processes into RAM, which requires focusing on allocation and deallocation. When more processes enter RAM, more allocation happens, and when they exit, deallocation occurs. Security is also crucial because multiple processes might interfere with each other. The operating system ensures that each process use only its allocated memory space. Now memory management techniques. Moving forward to memory management techniques. Operating system uses various memory management methods to handle primary memory efficiently. As we established, degree of multiprogramming is crucial. We need maximum process in main memory, so CPU always has process available for execution. Memory can be visualized as a large area of bytes where every byte has an address. We divide this memory through partitioning. Our main objective is keeping maximum process in ready state. When maximum process are in the ready state, we can pick one for running state. If that process gets blocked or request IO operation, we immediately have other process available. Consider a simple example. Writing a C program that reads content from file xyz.txt. During execution, this program uses a read system call. call. Now, since the file is located on the hard disk, this becomes an IO operation. When a running process requests to read this file, CPU allows it to perform IO, and then the process temporarily exits CPU. When one process performs IO, another process in the ready state can immediately use the CPU. Memory management techniques are broadly classified into two types: contiguous and non-contiguous memory allocation. In contiguous allocation, we have fixed partitioning and variable partitioning. Let's understand the basic concept. We divide RAM into memory blocks or partitions. When a process comes, we place the entire process in a particular block. Since operating system occupies some RAM area first, we use the remaining portion for processes to achieve high degree of multiprogramming. Continuous memory allocation means providing continuous memory address to similar process. If a process has 4 blocks B1, B2, B3, B4, we provide continuous address allocation. Fixed partitioning involves pre-dividing memory into slots of particular size, while dynamic partitioning allocates memory when processes arrives based on their specific requirements. Now, non-contiguous memory allocation means we don't provide continuous allocation. A process can be divided into different blocks and stored at a different memory location. For example, if process P has partitions P1, P2, P3, P4, these can be placed at a separate location in memory. P1 at one location, P2 at another location with other processes. This approach uses paging, multi-level paging, inverted paging, segmentation, and segmented paging. So now we will discuss in contiguous partitioning, we will discuss fixed partitioning. In fixed partitioning, the number of partition is fixed beforehand during system configuration. This is the key characteristic. We decide the number of partitions when setting up the system, but the size of each partition can be same or different. Let's examine this with diagrams. First, operating system occupies some RAM space, then we divide the remaining portion into fixed size slots. For example, we might create 4 partitions of 8 MB each. When processes arrive from secondary memory, they can be accommodated in these predetermined partitions. The important constraint is that processes should be either equal to partition size or smaller, because contiguous allocation doesn't allow spanning. Spanning means place part of a process in one partition and the remaining part in the another partition. This is allowed in non-contiguous, but in this contiguous, this is not allowed. The entire process must fit in the one partition, or we need to bring smaller processes. We can also have different size partition, for example 4 MB, 8 MB, 8 MB and 16 MB partition. This provides more flexibility for accommodating various process sizes. Let's analyze different scenarios. When a 4 MB process P1 arrives and all partitions are empty, we place it in the first available partition. If P1 is 4 MB and the partition is of 4 MB, now it fits perfectly. This is the best case scenario. However, if a 2 MB process arrives in a 4 MB partition, P1 uses only 2 MB but goes the entire partition. The remaining 2 MB cannot be used by other process because the entire partition is allocated to one process. The wastage is called internal fragmentation. If a 7 MB process P2 arrives in an 8 MB partition, it occupies 7 MB, leaving 1 MB unused. Again, this is 1 MB cannot be utilized, creating internal fragmentation. This is called internal fragmentation. Now, consider a 32 MB process trying to enter our system where maximum partition size is 16 MB. This process cannot be accommodated anywhere. There is a limit on process size. Now, the third limitation is what? Since we have fixed 4 partition, we can accommodate only maximum 4 processes simultaneously. If we want 5 or 6 processes in the RAM, it's impossible. This creates a limitation on degree of multiprogramming. With variable sized partitions 4 MB, 8 MB, 8 MB and 16 MB, we can accommodate processes up to 16 MB, providing more flexibility, though internal fragmentation is still occurring. Now consider this scenario: P1 2 MB, P2 7 MB, P3 7 MB, P4 14 MB. These are allocated and creating internal fragmentation of 2 MB, 1 MB, 1 MB and 2 MB. Total 6 MB wasted. Now if P5, let's say 5 MB arrives, it cannot be accommodated despite having 6 MB total free space, because this space is fragmented across different partitions. This is what? This is external fragmentation, having sufficient total memory but inability to use it due to contiguous allocation constraints. Fixed partitioning has one advantage: it's easy to implement since partitions are predetermined. It suffers from 4 major problems: internal fragmentation, process size limitation, degree of multiprogramming limitations, and external fragmentation. This method was used in 1960s. Now moving forward to variable partitioning, we will call it dynamic partitioning. Variable partitioning allocates a space to processes only when they arrive in RAM. We keep RAM empty initially, and when process comes, we allocate exactly the space they need at runtime. This contrasts with fixed partitioning, where we create partitions beforehand. Think of it like ordering a pizza. Fixed size partitioning is like pre-cut pizza slices, where someone like wanting more than one slice or less than one slice faces wastage. Now variable partitioning is like bringing whole pizza and cutting according to each person's need. Now let's examine how this works. When process P1 of size 2 MB arrives, we allocate exactly 2 MB, no wastage occurs. Process P2 of size 4 MB gets exactly 4 MB allocation. Now process P3 of size 8 MB gets exactly 8 MB. This eliminates internal fragmentation completely. Now variable partitioning provides these major advantages. First, there is no internal fragmentation since we allocate exact memory requirements. Second, there is no limitation on degree of multiprogramming. Since we don't pre-partition memory, we can accommodate as many processes as RAM size allows. Third, there is no limitation on process size. If a 64 MB process arrives, then RAM has sufficient space. We simply allocate 64 MB. Now, problems arise during reallocation. When process P2 4 MB exits, it creates a 4 MB hole. If process P4 4 MB also exits, it creates another 4 MB hole. Now if process P6 or size 8 MB arrives, we have total 8 MB available, 4 MB plus 4 MB, but since holes are not contiguous, we cannot accommodate P6. Like this is external fragmentation. We can use compaction to solve external fragmentation. Compaction means moving all processes to one side and gathering all holes to another side, creating one large contiguous hole. It requires stopping running processes temporarily, which disrupt the execution. Now copying and moving process take considerable time. Now moving forward to allocation algorithm in contiguous memory management. When we have multiple holes in memory and new process arrives, we need algorithm to decide which hole to allocate. There are 4 primary algorithms: first fit, next fit, best fit and worst fit. Consider a memory layout with several processes already loaded and multiple holes of different sizes available for allocation. First fit algorithm. First fit allocates the first hole that is large enough to accommodate the incoming process. For example, if process P1 of size 15 KB arrives, first fit searches for the beginning and stops at the first hole that can hold 15 KB. If it finds the 25 KB hole first, it immediately allocates the P1 like there without searching further. The advantage here is simplicity and speed. Minimal searching time since we stop at first suitable hole. The disadvantage is potential for creating large unused partitions since we are not optimizing for space utilization. Now next fit algorithm is a modified version of first fit. Instead of always starting search from the beginning, it maintains a pointer to the last allocated hole and starts searching from there. If we allocate P1 to a hole, we keep pointer there. This approach avoids repeatedly searching the same initial holes, potentially providing better distribution of processes across memories. Now the next is best fit algorithm. Best fit searches the entire memory to find the hole that result in minimum internal fragmentation. For a 15 KB process, it examines all available holes 25 KB, 40 KB, 20 KB and etc. and selects the 20 KB hole because it leaves only 5 KB unused, which is minimal. The advantage is reduced internal fragmentation and efficient space utilization. The disadvantage is slow performance since it must search the entire memory before making allocation decision, and additionally it tends to create many small holes that may be too tiny for future processes. Now worst fit algorithm. Worst fit is opposite to best fit. It selects the largest available hole to maximize remaining space after allocation. For a 15 KB process, if a hole is 25 KB, 40 KB, 20 KB and 100 KB are available, it chooses the 100 KB hole. It's also slow since it must search entire memory. Now if we compare them, first fit is the most practical algorithm due to its speed and simplicity. It's fast because it stops searching once a suitable hole is found, making it efficient for real-time systems. Next fit provides slight improvement over first fit by avoiding repeated searches of initial memory areas, though the benefit depends on memory usage patterns. Best fit minimizes space wastage but creates many tiny holes that might become unusable. It's also slow due to complete memory traversal requirement. Worst fit attempt to maintain large hole for future allocation, but it is very slow. Now in practice, first fit often provides the best balance of speed and reasonable space utilization. The choice of algorithm can depend on specific scenarios. Sometimes worst fit might work better, sometimes first fit. The key is understanding how each algorithm operates rather than memorizing which is the best. These algorithms form the foundation for memory allocation in contiguous memory management system. Each will distinct trade-offs between allocation speed and space utilization efficiency. So that's it for this video. We will meet in next video. Until then, bye bye.